All right, in this lecture, we're going to kind of move away from further analytical stuff of Laplace transforms, namely transfer functions, and we're going to do a thing that's called composing Laplace transforms for wacky functions. And why would you want to do that? Well, I'll explain here in a moment. This does show up. And so let's take a look. What is the, I need one new property for a Laplace transform so I can do this. And so what is the Laplace transform for a time delay? So here, suppose you have a function, and here's the Laplace transform of it, so you know it. So if you had a unit step, you have this, and so you have a unit step on one side, and this side you have 1 over s. Okay, so given that, then the Laplace transform of that original time function delayed by some amount t0 is the same f of s times e to the minus st0. So whatever your time delay is, you have e to the minus s times your time delay. Okay, so now we can start to contemplate this, because here's the thing. Let's just talk about this piece right here. Here's a function. I want to get the Laplace transform of this function, and then I'm going to delay it by 3 seconds and get that one. All right, this is a very normal input. I turn this machine on for a certain amount of prescribed amount of time, and then I turn it off. Step up, step down. You will not find this in a Laplace transform table. So we need to be able to get a Laplace transform for this, let alone delaying it to make this one. And so this delaying property is very helpful. So let's start with the original signal. What do you see? This is what we're going to see today is extremely visual. You got to let the picture talk to you. So at time t0, I have a step up, and that goes on. And at 2 seconds, I have a step down. All right. Now, the way Laplace transforms work is once they start, they never stop. They go on forever. So to make this, I need 2-step inputs. I need a step up happening here and a step down equal to this height at 2 seconds. So, and that's what this says. I have a step at time 0, and I have another step input that happens 2 seconds later. Okay, so you can kind of look at it as you have a step that goes up and it goes on for time, and then right here you have a step that goes down, and they cancel each other. All right, so you can see once the step input happens, it goes on forever as far as Laplace is concerned. So if you want to bring it back down, you need to have another step that goes, when you're ready, in the exact opposite direction. So that's what this shows. Here's 1 over s minus 1 over s times e to the minus 2s, and that gives us this signal. So now I just want to delay it by 3 seconds. Well, that's just as easy as doing that. If I take this signal, which is that, multiply by e to the minus 3s, it takes this and blasts it back by 3 seconds instantly. This is a powerful tool, because when you have to have inputs, and this is where this, in the real world, this is where this tends to come up, and you have to delay things, and you're doing things that are all synced and stuff, you're turning them on, turning them off, this is the tool that allows you to do this, and it's as simple as what we see here. Now, let's use this for some more creative problems. So consider the following signal. All right, maybe you don't want to have the system jump up. Maybe you want to have it gradually come up to some level, work for a certain period of time, and gradually bring it down. Things like this do happen. Okay, so here I have it starts at time equals 0, it goes up to a half, stays at a half, drops down. So that's 3-second signal. I need a Laplace transform of this that I can apply to some machine transfer function. So this is the input. Okay, so let's look at what we have. We have a ramp function. Okay, slope is a half. A generic ramp has a slope of 1. But a generic ramp function is 1 over s squared. That's the Laplace transform. Okay, so when you go to do something like this, you need to break it down into Laplace transform pieces that you already know or have. So, and the best way to do this is just show it in a picture. Once you see it, you kind of can't unsee it. It's really easy. So I'm going to have multiply this by a half, so that becomes 1/2 over s squared, or 1 over 2s squared. So we have a ramp coming up, starting at 0. That's this piece. And then it goes on forever. I want to undo that at time 1. I want it to level off. Well, now I just have minus t over 2 start at time equal to 1. And so from here on forward, this minus that levels off, cancels. At time equal to 2 seconds, I want it to start coming down. No problem. I have another minus t over 2 that comes down. So now this started it up, this leveled it, this brings it down. But when I get to time 3, I want it to stop. So that means I need another one going up to undo this one, cancel it. And then it would be flat from here on out. So when you do these problems, you're making this up using signals that go on forever. And so you're constantly undoing and stuff like that to achieve what you want. One going up, one going down, another going down, one going up will make this signal. Okay? Once you have that, we'd simply use our known Laplace transforms and our time delays. And so Laplace transform of t over 2 is 1 over 2 s squared. That came out as a cube. That's wrong. Or maybe it was a 2 and it's just sloppy. I couldn't tell you which one it is. Okay? 1 over 2s squared. There it is. All right? So this is the basic signal. I have 4 of them going up or down. So now I just start building it. Here's the first one. 1 over 2s squared going up. Now at 1 second, minus, I have the same signal going down forever. At 2, I start another one going nominally down. And then at 3 seconds, 1 over 2s squared e to the minus 3s, I start one going up. That levels them all off, and I get that signal. Not hard to do. The key to doing this is just take the time to make up the signal you want using various functions that go on forever, and they would start at, say, 0, and you just delay them out to where you want them to happen to add up to give you what you have here. So that's what that is. We're going to do several more problems here just to get some practice at this, and I'll see you soon.